Welcome to the deep dive. Today we're jumping into something really quite mind-bending, wave-particle duality.
Exactly. It's this core quantum idea that things we think of as particles, like electrons or even photons, which make up light, can sometimes behave like particles, tiny points.
Yeah, like little billiard balls.
And other times like waves spread out and interfering. It really challenges our basic picture of reality.
Definitely. And we're using the source wave-particle duality, quantum reality explained, to sort of guide us through it, the mission. Make this make sense, hopefully, and show you why it's such a fundamental concept.
So where do we start? It actually goes way back.
Yeah, the history, right.
Back in the 17th century, you had this big debate. Newton thought light was particles, these tiny corpuscles.
Okay.
But then Huygens argued, no, it's a wave, like water waves spreading out. And for a long time, well, Newton's view mostly won out.
So particles, definite spots, waves, spread out energy. How did they possibly merge these two?
Well, the whole game changed in the early 20th century. Quantum theory started emerging, and experiments. Einstein, in 1905, explained the photoelectric effect.
Right. Light hitting metal knocks electrons off.
Exactly. And his explanation showed light behaving as if it came in discrete packets of energy. We call them photons now. So, boom, evidence for light as particles.
Okay, so case closed. Light's a particle.
Ah, not so fast. Because then you have Thomas Young's double-slit experiment. That's the classic one.
The double slit. Explain that again, because it's key, isn't it?
Absolutely central. Imagine firing something light or even single electrons at a barrier with two thin slits in it. Behind the barrier, there's a screen to see where they land.
Okay, so if they're particles, like tiny marbles, you'd expect just two lines on the screen, right? One behind each slit.
That's the classical expectation. But that's not what happens. If you just let the electrons fly without watching which slit they go through, you get this pattern of multiple bands on the screen, bright and dark stripes.
An interference pattern.
Precisely. That pattern is a telltale sign of waves interfering peaks adding up, troughs canceling out. It's as if each electron somehow goes through both slits at once, like a wave, and interferes with itself.
That's weird. But what happens if you try to see which slit it goes through? Like put a detector there.
And this is where it gets even stranger. The moment you put a detector at the slits to figure out, did it go through the left or the right? Poof. The interference pattern vanishes.
It just disappears.
Completely. You just get the two simple bands, exactly like you'd expect for particles. The act of measuring, of observing which path it took, seems to force the electron to behave like a particle. It's like reality changes depending on whether we look.
Wow. The observation itself changes the outcome. So is this weirdness just for light and electrons? Tiny quantum things.
Well, for a while, maybe people thought that. But then came Louis de Broglie in 1924. He had this really bold hypothesis.
Which one?
He thought, well, if waves can act like particles, like photons, maybe particles can act like waves. He proposed that all matter has a wavelength, inversely related to its momentum.
Momentum, meaning like its mass times its velocity, it's oomph.
Yeah, basically it's oomph. More momentum, shorter wavelength. And this wasn't just a guess.
It was proven.
It was. In 1927, Davison and Germer showed electrons diffracting off a crystal lattice. Diffraction is purely a wave phenomenon, so yes, electrons can act like waves. This duality isn't just for light, it's fundamental to all matter. You have a wavelength, I have one, this table has one.
But they're just incredibly tiny for big objects, so we don't see ourselves acting like waves.
Exactly. Too small to ever notice in our macroscopic world. But it's there.
Okay, so this wave-particle duality is real, it's fundamental. What does that mean for reality? What are the big takeaways?
Well, it fundamentally shook classical physics. It implies that quantum objects don't really have definite properties like position or momentum until you measure them. Before that, they exist in a kind of haze of possibilities described by probabilities.
So it's not just that we don't know where the electron is, it's that it isn't definitely anywhere until we look.
That's the standard way of thinking about it, yeah. The Copenhagen interpretation, largely. The measurement kind of crystallizes one reality out of the possibility.
Which raises huge philosophical questions, doesn't it? About reality, observation.
Oh, absolutely. And there's no single answer everyone agrees on. You have Copenhagen, but also things like the many worlds interpretation, suggesting maybe all possibilities happen just in different parallel universes. It gets pretty wild.
Okay, deep breaths. So wrapping this part up. Particles act like waves. Waves act like particles. Observing them changes how they act, especially in that double-slit experiment. And this forces us to accept that the quantum world is just fundamentally probabilistic and weird.
That's a good summary. It's a reality that's just very different from the one we experience day to day.
So, a final thought for you listening. If observing something tiny, like an electron, can literally change its behavior, could observing things on a larger scale, maybe even observing ourselves or situations, have effects we don't normally consider? Something that maybe ponder on your own.